All right, so taking a look at number 12 in chapter 14. So in this one, it says a student has the following 8 compounds in unlabeled vials. Big no-no. Identify each structure by matching it with its characteristic IR or mass spec trait. So they give you all the structures of all these different things. So let's look at these. And we'll just go through them piece by piece. So the big thing people have been worrying about with a lot of this is, how do I know which peaks matter in IR? How can I determine between 2 compounds, right? So if you have a list of things that are possibilities, right, you can do some process of elimination for most of these, right? It's not that you need to know every peak in the IR what it means, but you can look at an IR and say, hey, this IR needs to have a C-double bond O. If the IR doesn't have a C-double bond O, can it be this compound? No. Right? So it's not that you need to know every peak in the IR, but you need to say, in this compound there needs to be an OH. If there is an OH in that IR, then this compound is still a possibility. Right? So it's not that you need to say, I know every single peak what it means, but you need to do a process of elimination with some of these. So another one. This is an alkyne. There is an iodide. And then the last one, there's 2 more. One with an alkene. And then one with a tertiary amine. So, just looking at these, right, these are all very different compounds. All right, you should look at these and identify them and be all very different. So let's zoom in on a couple of them. So chlorine. What's unique about compounds with chlorine in a mass spec? Who remembers? What's unique about chlorine? They have isotopes, right? And not only do they have isotopes, chlorine exists as chlorine 35 or chlorine 37, and it's a particular ratio they exist in. They exist in a 75% of all the chlorine on this planet is 35, and 25% is 37. That means the molecular ion peak, right? So if we have a peak like this, our M peak, which represents a molecular ion, we're going to have an M plus peak, M plus 2 peak, that is 1/3 the height, right? It'd be a 3-to-1 ratio. If you have a chlorine, the molecular ion peak, the M peak, is going to be 3 times the height of an M plus 2 peak because chlorine exists in these natural isotopes. Right? So that's really indicative of chlorine. In the mass spec, you'd see a 3-to-1 ratio of your molecular ion. Also, let's look at bromine. What makes bromine unique? Bromine, same deal, except it's not quite the same deal. Bromine 79 and bromine 81 exist, but they don't exist in a 75-25 ratio or 3-to-1 ratio. They exist in a 50-50 ratio. So then, in this case, your M peak, your molecular ion peak, and your M plus 2 peak are going to be exactly the same height. So your molecular ion and your M plus 2 peak are now exactly the same height. So that's how you know you have a bromine. Does that make sense? The isotopes, it's like the dead giveaway. A chlorine, you'll see a 3-to-1 ratio in your molecular ion, and bromine, you'll see a 50-50, a 1-to-1. You can look at IR here and say carbon-chlorine stretch comes in at some place, right? A carbon-bromine stretch. But the best way for this way is mass spec, right? NMR would be even easier yet, because NMR, right, you'd be able to, actually see the frequency would be different, right? Because chlorine's more electronegative, so you'd expect the H here to be more shielded or deshielded? Deshielded, because it's pulling away electron density. So it's taking away the shields. The electrons are the shields. So this would be more deshielded. This would be more shielded.
Would have like a higher
This would have a higher frequency, not a higher peak, a higher frequency. The peaks would be the same height because they both represent 1H. But the frequency, the ppm, would be different. Okay? What? Easy one, alcohol, OH. What are you going to expect to see? Big old fat peak in the IR, right? A big stretch around, was it 3,400 to 3,200 approximately? See that big, strong, intense stretch. That's what I would expect. So if you don't have that, you don't have that molecule. Right? That's the other thing to remember too. Is when you have these molecules, you have to have all the possible functional groups. So this molecule here has an OH, so you'd have to see an OH. It also has a lot of sp3CHs. You'd also want to see a lot of sp3CHs around 2950. Got to see them all. Right? You can't just say, oh, I see a bunch of sp3CHs, this must be the right molecule. If you don't have the OH and the sp3CHs, it's not the right molecule. Right? It has to have all the possible functional groups. You can't just have one. It has to have them all. How about this one? A carbonyl, a ketone. What would you expect here? What's going to be indicative of this molecule in either IR or mass spec? So you see, no, not past 3,000. What kind of CHs does this molecule have? This one right here. Only sp3CHs. So there should not be anything past 3,000. It should all be CH peaks, right? There should be sp3 hybridized CH peaks around 2950, right? What other peak would you expect to see in the IR? C double bond O. Which kind though? What kind of functional group is this? It's a carbonyl. What type of carbonyl is this? It's a ketone. Aldehydes have an H on one side. This is a ketone, has two carbons. And ketones come in a particular spot. This is a saturated ketone, right? Notice how it's not conjugated? Are there any pi bonds next to it? No. Do pi bonds next to ketones or aldehydes affect the frequency it stretches at? Yes. So this one should stretch at C double bond O for a ketone, and it should be around 1710. And that's in your table, your specific IR table. Saturated aldehydes and ketones, I think it's around 1715, maybe. Saturated meaning it's saturated with hydrogens. There's no pi bonds. Right? Remember what happens if there's pi bonds? Right? Then there's resonance, and then that changes the frequency from being, right, a shorter bond, having some single bond character, and we talked about how that affects frequency. Good. Moving along. What do we have here? So in this molecule, if I'm talking about this is a alkyne. So where does an alkyne CC stretch at? So an alkyne CC stretch is where? About 2200, 2100? Where is it at? 2100? Right, so when we talk about stretches and bends, we're just talking about the different ways the molecule can stretch, like move. Right? Sometimes the molecule stretches, the bond stretches, and sometimes the molecule bends. So there's the same functional group, like a CH bond, can have both a stretching frequency and a bending frequency. Right? So things can have both stretching and bending frequencies at different places. So the same functional group can have different stretches or bends. What other peak is going to be really indicative here? Not just the CC's triple bond stretch. What other peak is going to be indicative or functional group here? So definitely have sp3CHs around 2950. That's around 2950. Nothing above 3000. What other kind of stretches will it have or bends? There's a big one staring you in the face.
Isn't it SP, just SP hybridized now?
SP what?
Well,
SPCH, right? There's an H here. Where do SPCHs come in? Table 13.5. Where are SPCHs at? The top, very top, 13.5. 3,300, right? And are they broad? They're pretty sharp peaks, right? Usually they're not broad, right? They're sharp. They're not like an OH, right? Some people, that's another question I'm getting a lot of. People are saying, hey, an OH stretch is around 3,300. How am I supposed to know the difference? What does an OH stretch look like? It's that big, fat, broad one. This stretch is going to be very intense and skinny, right? So the intensity of the stretch, where the stretch is at, and then also how it looks will matter, right? OHs are broad. Carboxylic acids are broad. And SPCH, tight and skinny. Good. What about the iodide? What are we going to do with that one? You can look for the carbon iodide stretch. What else could you look for? This is a little trickier. It's in a mass spec one. So iodide, the way to think about this is a carbon iodide bond very strong. Is a carbon iodide bond? Why is it not very good? Why is it not a very strong bond? Why is it a reactive bond? There's less orbital overlap. So if you were doing a mass spec, would you expect that carbon iodide bond to last very long? Or do you think that bond's going to be breaking off pretty fast? It's going to break off pretty fast, right? In a mass spec, right, you're going to lose one electron right away. But then an iodide, do you think an iodide is going to want to undergo what kind of cleavage? Well, if I drew this after it went through the electron beam, what kind of cleavage is an iodide going to want to undergo? Heterolytic or homolytic? Remember what it says about bond strength. If you have a strong bond, are you going to want to undergo homolytic or heterolytic? So we just talked about this bond right here. Is there a lot of orbital overlap there? No. Does iodide like having a plus charge? No. What kind of cleavage is this iodide compound going to undergo? Heterolytic or homolytic? Say it louder. Heterolytic, right? It's going to be much more like bromine, right? Bromine undergoes heterolytic cleavages. Chlorine, because chlorine's smaller, will undergo heterolytic and the homolytic cleavages. Remember? So bromine doesn't undergo alpha cleavages at all, right? Because it's so big and that's a pretty weak bond. So iodide is also, right, is even more so, more likely to undergo a heterocleavage, heterolytic cleavage. Right? Form a secondary carbocation, and then the iodine, right, with 7 electrons around. Right? Remember we talked about carbon versus bromine? Or chlorine versus bromine? Right? Chlorine and carbon form a pretty strong bond. So it's possible to do an alpha cleavage, a homolytic alpha cleavage. But bromine, because bromine's already so big and that bond's already so weak, it just never does alpha cleavages. It just does heterolytic. And iodine's even worse, right? Iodine's even bigger. So iodine's only going to undergo heterolytic cleavages. So the best way to identify this molecule is you'll say, how much does iodine weigh off the top of your head? What's the molecular weight of iodine?
127.
127. So whatever you have, right, you should see a big peak for the normal mass minus 127, right? Because if you looked at this molecule right here, the most likely fragment would be this bond breaking, which would be the molecular weight of this minus 127. So that'd be the base peak. This would be the base peak, which is molecular weight M minus the molecular weight of iodide, 127. That makes sense? All right, 2 more left to go. So now we have cyclohexene. So what's unique about this molecule? There's not a lot of functional groups here, right? But what is unique about cyclohexene? What will you see? What kind of functional groups are there? C-double bond C, and where does C-double bond C? Where is that at? Around 1650? Right, you'd expect that around 1650. What else would you expect with this alkene that's different than any of the other ones we've seen so far? There'll still be what kind of CHs? There'll still be sp3 CHs, right? But there's been a lot of them that have sp3 CHs. They're still at 2950. What does this have that the others haven't had? sp2 what? sp2 hybridized CHs. So we've had sp hybridized CHs, but now we have sp2 CHs. Where are those at? The sp2 CH stretches where?
Over 3,000.
Yep, but where exactly? It's around 3,100. Right? So you expect to see a sharp peak around 3,100, right? OHs are broad. All the CH stretches are very sharp. Okay? Good. And then our last one, the nitrogen rule problem. So we refer back to the nitrogen rule. This molecule has how many nitrogens? 1. And so that is 1 is an odd number. So the molecular ion for this molecule right here would you expect to be odd as well. So this would have a odd molecular ion. We call the M plus peak. Because it has 1 nitrogen. So the nitrogen rule states if you have an odd mass, an odd molecular ion, right, the farthest right peak, the heaviest peak, if you have that, that means you have an odd number of nitrogens. 1, 3, 5, 7, something like that. If it's an even molecular ion, an even heaviest peak, you either have 0, 2, 4, or 6. So some people had benzylamine for their unknown. There was an amine. We did have an amine for this last lab. So some people should have had an odd molecular ion for benzylamine. Yeah, I think they did. Because there's 1 nitrogen in that. So this is the one problem you need to know the nitrogen rule. So we're going to take a look at an alpha cleavage. What happens in an alpha cleavage? So the first thing that happens in a mass spec experiment, of course, is what? You submit your molecule to the electron beam. And the electron beam knocks an electron out. When you have molecules that have lone pairs, those lone pair electrons are the easiest ones to knock out. So let's knock out one of those. So I just show electron beam, knocking it out. That's not really what happens, but it's fun to draw it that way. So now we have where there was an electron, we put a plus charge, right? We've lost an electron. Now in this case, we have one of 2 pathways we could go. We could do a heterolytic cleavage, or we could do a homolytic cleavage. Right? The carbon-oxygen bond is strong enough, right? That's enough orbital overlap there that we certainly can do a homolytic alpha cleavage. Right? Remember we talked about bromine and iodine, right? They don't do alpha cleavages or homolytic cleavages because that bond is already so weak. They just do a heterolytic cleavage. So let's do an alpha cleavage first. So alpha cleavage. That means we're breaking the bond to the alpha carbon. The alpha carbon is defined as, if this is our functional group, the alpha carbon, right? Either of these is an alpha carbon, and then this is a beta carbon, right? So I purposely made this ether symmetrical so it doesn't matter which side I choose, right? It'd be the same either way. So I chose this purposely. So if I label these alpha and beta, so we're going to break the bond between the alpha and the beta carbon, right? Alpha cleavage. So let's draw those electrons in. All right, we're going to break the bond between the alpha and the beta carbon. All right. So we're doing a homolytic cleavage, right? All alpha cleavages are homolytic, meaning what? What? We're moving how many electrons at a time? 1, right? We're moving more than 1 electron at a time, but we're using fishhook arrows, right? We're moving 1 electron, and each arrow is 1 electron. Right, so what are we doing here? So this electron is going to go there between the oxygen and the alpha carbon. Another electron's going there. That's going to form a new pi bond, right? How many electrons in a pi bond? How many electrons in a pi bond? Pi bond? 2, right? Double bonds have 2 bonds, hence the word double. One of them is a sigma, one's a pi. Here we're making a pi bond. How many electrons in any bond? How many electrons in any bond? 2, right? So we're making a pi bond, which has how many electrons? 2. This other electron is going to go to the beta carbon, and that's going to be the radical, right? Anytime you do a mass spec, what part of the mass spec do you detect? What do you detect in a mass spec? Cations, right? So we're going to break this up. We're going to have a radical and a cation. At the end of the day, you always have to have one part's a radical, one part's a cation. All right, so that breaks off. So where did the electrons go? This side didn't change at all. That lone pair didn't change. We should have a new pi bond. The plus charge stays here. This is the alpha carbon. The alpha carbon has how many hydrogens bonded to it? How many hydrogens are bonded to that alpha carbon? 2. There always were, right? Up here as well, right? We didn't break any bonds, any hydrogen bonds, so we broke a carbon bond. So now we have the beta carbon is at CH3, and that's where that radical, that one electron, ended up. So these are the 2 pieces we have. Are we going to see the radical in the mass spec? No. What we're going to see in the mass spec is this cation. Right, that's what we're going to see in the mass spec. All right, so that's one possibility, right? When we do a mass spec, we send in thousands, if not millions upon millions of molecules into the mass spectrum. Right, we're only using micrograms, but even a mole of molecules is what? 6.02 times 10 to the 23rd, right? That's a lot. That's a lot of molecules. You know mole stands for what? What does mole stand for? Molecules. I'd figure that. I only learned that when I was teaching Gen Chem too. Never thought of that myself. Right? So there's a lot in there, right? Every mass spec, we're putting a lot of molecules in there. So a lot of them are going to break up different ways. So this is just one possible way this could break up. Right? So let's draw this again. I'm going to redraw that. So one possible way I showed is a homolytic cleavage. It's alpha cleavage. The other possible mode that could happen is a heterolytic cleavage. Now in a heterolytic cleavage, just like it sounds, we use double-headed arrows. Right? Each arrow represents movement of 2 electrons. So in this case, it doesn't matter which side we go here. I'm going to draw 2 electrons in. And instead of the oxygen, right? The oxygen hates having that plus charge. A heterolytic cleavage, we're just going to break the bond to oxygen whenever it's bonded to, in this case, and give it to those 2 electrons. And now, right? So the oxygen got back those 2 electrons. Right? And the other piece would now have the plus charge. Right? We now have the plus charge because it lost 2 electrons. And what part would you see in the mass spec? Would you see the oxygen piece or only the carbon piece? Just the carbon piece, right? Because this is the part that has the cation. The plus, we only detect the cations in mass spec. So this is a heterolytic cleavage. So in this case, right, you got a million of these molecules. You'll make some of this. You'll make some of these. You'll see some of these. Right? These are cations too. That's a molecular ion. Right? You'll see a bunch of different ones. And whichever one's the greatest is called what? Whichever fragment's most likely, what do we call that? The base peak. Right? The most likely fragment, of course, is the base peak. Right? The most likely fragment is the base peak. So number 2 on quiz number 2 from 2014. So it says, what is the name of the peak that rises from the most likely fragment? That's the base peak. Draw the most likely fragment of the molecule below. Explain your answer. So let's see. So we have this molecule below. I like to number my carbons, because that's what you should do. 5, 6, 7. So which bond is most likely to break, and how do we tell that? So the first thing that happens, right, is we lose an electron, right? We go to dot plus, right? An electron beam knocks an electron out. We don't know exactly where it's at. When we don't have lone pairs, we don't know where it's at exactly. So we just put dot plus. So we lost one electron. Which bond should I break here to form the most stable fragment? All right, so which bond do we want to break here? What kind of fragments are the most stable? That's the other part of the question. What kind of fragments are the most stable? So we're going to make a carbocation, right? So the question really is asking, do you understand what? Carbocations. In particular, the stability of them. What kind of carbocations are the most stable? Tertiary. Now let's think about what that means. Now why, if I put a plus charge here, that carbon is considered a tertiary carbon. What do we mean by tertiary? This carbon is bonded to 3 other carbons. Now why does that make it more stable if it's a carbocation? It's because of hyperconjugation. Now let's take a look at a picture. Hyperconjugation, we call them hyperconjugation buddies. Now this one has 9 hyperconjugation buddies. So let's draw a carbon, sp2 hybridized, right? Carbocations are sp2 hybridized. All right, sp2 hybridized. Now in this case, it has 9 hyperconjugation buddies. Hyperconjugation is bonds that are 2 sigma bonds away. Again, we don't draw our hydrogens in here, but that should matter. 2 sigma bonds away. Now notice, right, 1, 2 away, right? Here's a carbon-carbon bond, but is this carbon-carbon bond? What kind of bond is that? Sigma or pi? Sigma, so it still counts, right? Right, so this 1, 2 bonds away, 1, 2 bonds away, 1, 2 bonds away, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. That's 9, right? A tertiary carbocation has 9 sigma bonds that are 2 bonds away, right? Whether that sigma bond's from a CH or a CC, it doesn't matter, as long as it's a sigma bond. So it has 9, right? It has 9 hyperconjugation buddies. 9 sigma bonds, 2 bonds away. See that? We convinced that this is the most stable carbocation? Yes? So now we go back up here and say, well, I want to make a tertiary carbocation if I can. Which bond should I break here to make a tertiary carbocation? There's a couple options. Which bond should I break?
1, 5, or 6.
1, so wait, tell me which numbers? 1, 5, or 6, 1 to 2, 1 to 2, 5 to 2, or 6. Yeah, I need to break one of the bonds to carbon 2. Not this bond. Well, I could break that bond too, right? If I broke this bond, I will make a plus charge on carbon 2, right? And that would be a tertiary carbocation. I could also break the bond between 2 and 3, right? And that would put a tertiary carbon on carbon 2. There's actually 2 options here. I only showed 1. So you could break any of these bonds, and that would put a plus charge on carbon 2, which would be a tertiary carbocation, and these would be radicals, right? So I'm going to draw 1. I'll draw 1 out for you guys. I'll shrink it and draw 1. So one of the possibilities could be the plus charge here, and then there'd be a CH3 with a dot, and if I number the carbons in, 1, 2, 6, 3, 4, 7, and then 5. Right, this is a radical, right? Every piece I'd have to have one part's the cation, one part's the radical, and I see the cation in the mass spec. Right, that's if I broke, in this case, that's if I broke between C5 to C2. I could also break other places, right? And still get a tertiary carbocation. That's the kind I want to get, right? That's the most stable because it has more hyperconjugation. Yep. So number 6, quiz number 2, 2014. So this has to do with what things affect IR stretches, right? So the bond length, right? Whether you have a single bond, a triple bond, a double bond, right? That affects things, right? The shorter the bond, the triple bonds, right? Shape at a higher frequency because the bond's shorter. But how does mass affect things, right? So then if you think about if your stretch, if my hands are holding something, one thing's heavy and one thing's light, which one can I go faster with? The light thing, right? I can stretch and bend the light thing easier, right? Because it essentially has less mass. So in this case, the oxygen versus the sulfur, right? The oxygen, right? What's the difference? Oxygen versus sulfur? Sulfur's lower on the periodic table, also meaning that it's also heavier, right? Has a higher molecular weight. So in this case, right, if you think about the oxygen and the sulfur weighs more. It's going to be harder for me to stretch it. It's going to be harder for me to stretch it. So that's going to mean I'm going to stretch it at a lower frequency, right? Less fast with less energy. So that's why it'll be a difficult stretch. So the higher wave number would be with this, because I can stretch it faster. Higher frequency. That's basically the difference, right? The difference between them is mass. That's the difference. So what else affects this? So this is showing how mass will affect IR. Right? The type of bond, whether it's right a CH like this, so hybridization also affects it, right? If this is an sp2 versus an sp3 versus an sp, oops, forget that, draw it better. Right, an SPCH, so hybridization affects it. Right, hybridization affects it because hybridization affects how long this bond is, right? So right, if we had a NC bond versus this one versus this, right? So the bond length, the shorter the bond, the higher the frequency, right? This is a shorter bond because this hybridization state is sp, so it's the sp orbital here, which is shorter and fatter. So the mass affects it, the bond length affects it, and then so can, right, resonance can affect it as well in different ways. Right, so resonance is the other way they can affect the IR stretches. And resonance doesn't always make it stretch at a higher or lower frequency. It just affects it one way or the other. If you can do resonance, it will affect the stretch, but not always the same way. So kind of concrete way, so how do we compare electron delocalization and induction? So the example we showed in class was an ester versus a amide, which is a really nice example. So you have an oxygen versus a nitrogen. So what do you guys know? What's the difference between oxygen and nitrogen? What's the major difference? Electronegativity. So who's more likely to donate lone pairs? Nitrogen is. So nitrogen's more likely to do this resonance structure. And what is this resonance structure, in this case, going to do to the C double bond O stretch? Is it going to make it go to higher frequency or lower frequency? It's going to lower it, right? Because what was a double bond, which is short, now, if I draw it here, it looks like a single bond, which is longer. So it has some single bond character. So it's going to stretch at a lower frequency. All right? So amides are at a lower frequency because of resonance, around 1665 approximately. Now, resonance doesn't always lower the frequency. It can do it the other way too. In this case, it lowers it. You got to actually draw the resonance structures. But an ester is at 1745. So it must not be that this is donating electrons and this has single bond character, right? Now the frequency all of a sudden is higher. So the more important player here is induction. This oxygen is pulling away electron density and tightening this bond, making it even shorter yet, which of course is going to make the frequency even higher. You tighten that bond up, it's going to make that frequency even higher. So this, the important factor is induction. Here was resonance. Right? Oxygen versus nitrogen have that big of a difference. Taking a look at number 28, kind of a UV vis question, not a UV vis question, saying which of these compounds will absorb light between 200 and 400 nanometers. So the tricky part here is you need to have pi bonds that are next to each other or that are adjacent, conjugated. But the tricky one is that you can probably see pretty easily, hopefully. The difficult one is this one, where all of a sudden I have an oxygen, right? And normally, this oxygen has how many pi bonds? 0 pi bonds. So then it's what hybridization state? Then you say it's sp3. It's not sp3 hybridized. It's choosing to be sp2. It's doing that so it can have a p orbital. And that p orbital then can have a lone pair in it and be part of this pi system. So the way to look at it, it would look like, there's the oxygen. So it's next to 2 pi bonds. And at this point, the oxygen has a choice. So it's going to choose to be sp2 hybridized. So it has a p orbital, and it can put the electrons, one of its lone pairs, into that p orbital. And that p orbital then can become part of this pi system and be conjugated. Right? So it's good to get the bonds away from each other as much as possible. It's better to be conjugated. It's better to be part of the pi system. So this oxygen is making the choice. It's saying, hey, I'm going to be sp2 hybridized. I want a p orbital. I want to have one of my lone pairs part of this pi system. I'm UV active. This is conjugated. That's what it's doing.